Suppose we have two Hermitian operators, and let's for fun just call them A and B. Then you can actually construct a generalized eigenvalue problem with them. So what is a generalized eigenvalue problem? It's very similar to a normal eigenvalue problem. So you have an operator operating upon an eigenfunction, and then you don't get back the same eigenfunction multiplied with the eigenvalue lambda. Rather, you get back an operator B operating upon the eigenfunction multiplied by an eigenvalue lambda. So that's a generalized eigenvalue problem. Now for the regular eigenvalue problem, we've introduced a variational expression. Obviously, you can also introduce a variational expression for the generalized eigenvalue problem. And the question is, can you show that this is the corresponding variational expression? So in the course notes, we did a very similar derivation, but there B was obviously 1 because it was a regular eigenvalue problem. To show that you understood how the derivation in the textbook went, do a very similar derivation, but now for the case where you do have the presence of this second Hermitian operator B. So let's proceed very similarly to what we did in the notes. We started by bringing the denominator here to the left-hand side so that we have h AH is equal to JH BH. And the reason we're doing that is because this way we don't have a denominator which we would need to expand in the Taylor series if we were to look at the first variation. So let's make our life easy and write the expression like that. Now what we're going to do is we're going to call this equation the starting point. So let's call this equation 1. And what we're now going to do is take that equation and perturb it, basically. So we're going to replace h by an h plus delta h, and that will give rise to a corresponding change from j to j plus delta j. So let's introduce that change. Let's see what this perturbation looks like. And then we have here h plus delta h. And then we have a operating on h plus delta h, but that's a linear operator, so we can write this as a operating upon h plus a operating upon delta h. So that's the left-hand side. For the right-hand side, we will have a corresponding change in j. So j plus delta j times, and then for the final factor, we have h plus delta h, b operating upon h plus b operating upon delta h. And let's call this second perturbed equation, equation number 2. So just like in the course notes, pause the video here, expand this expression, subtract the first equation, and see what you can learn about delta j. So let's get to work here. If we expand this thing over here, we will end up with 4 terms, 2 times 2. The first term will be a term h and then ah over here. But if we subtract equation 1, that's exactly the term we find over there. So this first term will vanish. But that's good news. So then we have 2 more terms. We have a first term delta h ah, and then its symmetric brother ah delta h. Okay. And then we have a final term, and that final term will be a term where there's a delta over here and also a delta over there. But that's the second order term. We're going to neglect that in favor of these first order terms, which only have a single delta. So we basically have an approximate equality over here. Good, that's the left-hand side. From the 4 terms, we only have 2 left. The right-hand side is a little bit more daunting because we basically have 4 times 2 terms over here. So we have 8 terms that we, in principle, need to worry about. So let's take things slowly and let's first focus on j multiplying this guy, and then later on we'll look at delta j multiplying that expression over here. So let's have a look at j multiplying this expression between brackets here. So we have j, And then we have a first term. Now the first term will be HBH, but that's the one we subtract from equation 1. So no need to worry about that. So we have left H plus B delta H. Okay. And then we have another one, J. And then we have delta H BH. Okay. So these are the two terms over there. The next thing we need to worry about is the fourth term, but that will be a term that has two deltas there. So we're just going to neglect that. And then what we still need to do is look at what happens when we have delta J multiplying this whole thing over here. Now we already have a delta over here. The first term that we have will be delta J times H and BH. So we keep that one. But all of the other terms will be higher order terms where there will be at least two deltas. So all of the other terms are just going to cancel. Good. One final thing that we can do here, of course, to make things a little bit nicer is we can move, for example, this B to the first factor so that it operates on the H. And we can do that because it's a Hermitian operator, of course. I already did something similar for the first terms over there with A. Good. So now that we have that, we can basically calculate what delta J is. So let's do that. Let's just rewrite this a little bit so that we have delta J equal to 1 over H plus BH. Okay. And then we have a set of terms. So we have delta H AH plus AH delta H. And then we have some terms involving minus J rather. Now we know what that J is, so we can resubstitute that here. So that's just our variational form. So that's H AH divided by H BH. That's our variational form. And then we have in between brackets two more terms of a very similar form. So we have delta H BH plus, running out of space here, BH delta H. Okay. So this is what we have here. And again, if you look into the course notes, this is very similar to an expression we have over there. The only difference is that now we have some B's that are appearing here. But just like in the course notes, we will also introduce this new variable G, which we will define in a very similar fashion. The only thing is that we need to add some B's at certain locations. For example, over here. But otherwise, it's extremely similar. And then we have AH minus our J, which is this ratio over here. So this is a ratio of two scalar products. So again, this is just a number, as you know. Then we have BH over there. So again, very much inspired by what we do in the course notes, just making sure that we add some B's where it's appropriate. Just by looking at that formula, we can see where we should do that. And then we come to the same conclusion that we can write our first variation, delta J, as sort of the average of delta H G plus G delta H divided by 2. And in case we're looking for a field distribution that minimizes this variation expression, then our delta J, our first variation, should be 0. Very importantly, it should not just be 0 for a well-chosen choice of field distribution, for a well-chosen choice of H. No, it should be 0 for all possible variations around that H. So this should be 0 for all possible delta H's that you can think of. Now, if that's true, the only way we can make this vanish for all possible delta H is, of course, if our G here is equal to 0. And that, of course, only happens if this thing between square brackets is equal to 0. So if AH is equal to h AH divided by h BH BH. Again, I remind you of the fact that this is just a number, it's just a scalar basically. And what we have here is indeed our generalized, if I can get rid of this pop-up keyboard, is indeed a generalized eigenvalue problem. We have AH times our lambda, so this is our eigenvalue lambda times BH. So we indeed see that the value that we get when we minimize our variational expression, our J becomes indeed the eigenvalue lambda. This is a straightforward generalization to the variational form for a generalized eigenvalue problem.